We're finishing 3-2B today during class. We're going to check A and B tomorrow, unless we have some time at the end of class, then maybe we'll check homework number 19 at the end of class. But right now, we're going back to homework number 18. 3.1, the one that you guys were like, we had a crazy day on Friday. Everything was going on, tests and quizzes, and so I just didn't even grade it on Friday. I said, hold on, let's grade it on Monday. Hopefully some of you guys got some time to catch up this weekend. I know, weekends you always have great plans. Sometimes they work out. Sometimes they don't, but it's time for us to get back into the mathematical swing of things. So, 3.1, remember, exponential functions, this entire chapter. We're solving little baby puzzles, but we have to learn the rules first. Let's grade our evens quickly, and then let's keep on going with logarithms today. So, number 2, transcendental functions, straight out of the notes. Number 4, natural exponential function, E is the natural number, straight out of the notes. You guys, I'll just give you a second on 10, 14, and 16. Remember, 14 and 16, they just give an extra explanation to say why. Number 10 was a strict plug it in your calculator. Real quick, is anybody having any issues with their calculators with exponentials or logs? You're okay? 14 is C and 16 is B. It's not dragging so good. Let me come over here. Number 24, the first puzzle of homework, I think, or at least the first even puzzle. For those of you that aren't totally ready to be grading right now, what property? What property? Remember, passing around the whiteboard during the drill? What property? Good, the one-to-one property. So how do they get 16 to be 2 to the 4th? Break it down, just factor it out, right? And then as soon as the bases match, what can we do with the powers? Good. Set the powers equal to each other. We ignore the base. We didn't cancel it out. We would need a logarithm for that. But we ignore the base. Solve, solve, solve. 34 was just a plug and chug into your calculator. You guys said that no calculator problems are going on. 52, the last even puzzle of homework. Did E make it that much harder? No. He's just a base. He's just a constant. Does anybody have in their brains what decimal approximation he is? 2.7? 1?
5?
8? 2, 8. Woo! Put it all together. 2.71828. He's just a number, like pi, so we gotta treat him like one. Hey guys, any more evens? That was bonus. I'm just gonna leave it up here for just a second. I think it was an extra credit line.
I never quit to do the homework.
Did you guys figure it out? For those of you that tried the bonus, when you add exponents, this is tricky, you're going backwards. When you add exponents, you multiply like bases.
Oh man.
When you add exponents, you're multiplying like bases. So you're going backwards from the property you guys learned, I don't know, a long time ago. Yeah. It's kind of rough though.
Yeah.
But then you simplify some stuff, you get it down to being a different form. But anyway, that was extra credit. That's not something you're going to see on a quiz or a test, but I thought it was pretty cool because it makes you use some properties. Jacob.
When you got extra credit, like if we did it, you get an extra point. Oh, baby.
Yeah. Each of the problems in homework are worth about a 4th, so you just get plus a 4th. Okay. Hey guys, do you have any questions on 3.1 on the odds? Okay. This homework is supposed to be pretty good because he's exponential. And remember, in notes, just stay right there in your spirals, just for a moment. But in notes on Friday, when we started talking about logarithms, remember why I said this property is kind of important? Which one does our brain process more naturally? Exponential. Yeah, totally exponential forms. That's why homework 3.1 wasn't meant to be super crazy hard. Our brains kind of think exponentially. Now, the extra credit one, number 76, yeah, that one was kind of above and beyond because it had algebra in there and a 2x and the exponent. But coming back, usually our brains deal with exponential a lot better than logarithmic. So remember, in section 3.2, we're trying to get our brains to process logarithms a little bit better. To that end, we just started. Mrs. Johnson looking out for me.
Mrs. Johnson.
Sorry, Cal.
Let's come back.
Makes me do puns. Reminds me of my grandma.
What? All right, come back in, kiddos.
My grandma.
On Friday, we transitioned from working with logarithms algebraically with equations and simplifying and properties. We dealt with some different puzzles, but we had just started dealing with logarithms graphic. I'm going to keep this on the screen for just 1 second. You guys go to your workspace, back to your time. We're going to finish our notes today. We're going to finish how to deal with logarithms graphically. But go to your workspace, go to the back of your spirals. I want you guys to name this one 3.2b warm-up. If you want to give it a little title, you can say logarithmic graphing. 3.2b warm-up, or you can call it logarithmic graphing. We got this down on Friday for a logarithmic graph. But what we didn't get to do is we didn't get to transform it. Now, we've done transformations this year already, right, guys? We've done like translations and dilations and reflections.
Yep.
We're just going to have to take this graph, the logarithmic graph, and do some of those transformations as well. Now, you guys did it with exponential in 3.1. We just graded that homework. You guys seemed okay. But we need to do it with logarithmic. But in the back of your spirals, I want you guys, we're all going to graph one together, but there's going to be 2 other ones I want you to try to graph using what you know about transformations, basically with us not even having done any notes yet today. Let's see what you can do. But first of all, before we graph the transformed g and h, let's go ahead and get the basic function, which is, or the parent function, which is f of x. So everybody go ahead and mark down this equation, f of x, log base 2 of x. If you want to get out some colors, you can, to keep them different from each other. You can also just use, like, I don't know, solid, dashed, bold. You guys have already done transformations this year, so you know what to do. But let's start with log base 2 of x. These are parent function. If you guys look at the other ones up here, they're all transformations of log base 2 of x. But you guys are in your workspace. I'm going to pull up the notes. Actually, we're already in our notes. But I'm going to go ahead and show that page that we talked about on Friday to help us get the parent function, okay? Logarithms. Remember, we're not super used to them, especially their graphs. But on Friday, we wrote down there are 3 key points to a logarithmic graph. And they're really the 3 key points of an exponential graph, but just switched because, do you guys remember the relationship between exponential and logarithmic? What's that?
Flip.
Yeah, they flip, but they flip across the y equals x line. Their x's and y's flip. What's the relationship of the 2 functions? What are they called if their x's and y's switch? Yes. They're inverses of each other, which means they undo each other. That was really helpful for our puzzles and for our solving, and we're going to keep on using that the rest of the chapter. But we can use that in the graphs too, because the x's and y's switch. So we know every logarithmic graph, including this one, log base 2, has, look right here, an x-intercept of 1, 0. So first, right away, we can, for f, put the point 1, 0. Any non-transformed logarithmic graph, whatever the base is, log base 2, log base 17, log base 523, I don't care, get the x-intercept 1, 0. Okay? Now, everybody pause for 1 second. Get out your composition books. You're supposed to have them when you do homework too, right? Open up to this page that I'm talking about because it got kind of small on the screen. It's going to be hard to read. Open up your notes. Find a logarithmic graph that we did on Friday. Can someone find for me one of the other important points on my graph? Chris.
0, 1.
Ooh, careful. You're on the exponential graph. Log would be 1, 0, and we actually already have that one written. A1. Now, what's our A in this one?
2.
Because A is the same thing as the base, right? Okay, so then we know we need to go over 2 and up 1 for our next special point. What's the third special point?
1 over
1 over A negative 1. So then AJ, what would that be for this log?
half,
Good. So I'm going to go to a half, which is just going to be halfway. Let's go down 1. Now, we've gotten our 3 special points, and we could be like, swoop, there it is, but we need one more thing before I really want us to do that. What's the one other super key important characteristic of a logarithmic graph besides the 3 special points? The asymptote. Question. Where is the vertical asymptote going to be for any logarithmic graph if it has not been transformed, translated, moved? So put it. Swoop, you got it?
It is.
Got it. Yeah, Jacob.
So that, top point, what's the point?
That top one is gonna be 2, 1, because it's always gonna be the base comma 1, because remember logarithms? When will 2 to what power? What would that argument be? 2 to the 1 will always be 2. If it was a log base 3 minus 2, 3 to the 1 will always be 3, 4 to the 1 will always be 4, et cetera, et cetera. If you guys are wondering, for like staff development stuff, teachers just need to go and observe other teachers so many times a semester. So if you have been seeing teachers pop in, they're just kind of checking out the list, but we're also trying to get into each other's classrooms and be like, hey, we like this, hey, we don't like this, or start a conversation about new things that we want to start implementing. So in case you're wondering, that's what people pop in from time to time. That's the parent function. I want you guys in your groups, you can start collaborating right away. Can you give me G and H just based on what you know about transformations? And I'll give you a hint. On G, I would start by saying you're adding 2 on the outside. I think there's going to be a vertical shift. There's a -1 on the inside. I think there's going to be a ready, set, go. Do the best you can. In your groups. Write it out first. What transformations are happening? Write it out first. What transformations are happening, and then try to graph it as a group, work together. I don't know. Yes. You're not what it seems. There we go. Wait, so 2 off the right? Yes. Then try to graph it.
Still kind of
So it's gonna be 2, 0. For one of those. And then it's going to be
2, 5.
when you're graphing it.
Sure. But wait, no, is it that one or? Hold on, give me a second. What do you mean, 3 0? No. I'm moving up.
Yeah, I don't know what the heck it's doing.
Oh, I'm just marking the points here.
Ah, dang it.
Yeah, what did you get? 3 0 and then. Isn't it just 1, right?
Yeah. And it makes sense because of the -1.
No, wait.
Seriously, when is Thanksgiving break?
Careful.
If it's,
Not one
wait
time.
a second.
Today's
Your brain is playing a trick on you. What's the sign in front
It's
of
not
the
2 0.
1?
It's 2 2.
So you could think of it as a +1, negative log of X +1.
Yeah.
Careful.
Can we just take it out? Yeah, you're right.
Why did you actually attempt?
I'm attempting.
Yeah, so you were.
This stuff is deep.
So just 2 2.
Deep stuff.
There's a half.
I'm just gonna write the words for G, you guys can check it, just the words.
Are you
It's a
kidding?
4 2. It's 1 2.
Oh my god.
It's a 4 2.
Oh, yeah. Where'd you get 14?
Someone help me. 14?
Okay, seriously, what'd you get? 42. Oh, 42, I was like.
Someone help me.
Hey, we got that, we got
You guys
that.
get the words for the first one? Did you
Yeah.
Right? It's 0. No, give me a second.
Careful, and the inside is always backwards.
Oh, got you. Oh, that's so loud.
I'm gonna go ahead and write out. I don't think people like the first or the second one.
I don't like either of them.
That's another way of writing the second one. Reevaluate what you wrote. Down 1 is definitely not what's happening.
Wait, high school.
High school dropouts.
No, it's not a bad thing. Like a lot of brains, they play that same trick, so that wasn't bad.
You know, I'm just gonna.
Up 1.
He doesn't want to be able to use it.
Okay, right? Just do it. Exactly right.
You got a pen on your pen. I put the pen on your thing. I thought you wanted to really say.
Did you say that we were really sick?
There was a shift up one, but question, what's the very first thing that we need to consider before the shift up one?
Reflection.
It's on the outside multiplying by a negative, so what kind of flip is it?
X-axis.
Good, x-axis, a vertical flip. A vertical flip. A vertical flip and a shift up one. A vertical flip and a shift up one. So let me go ahead and sketch these and see how you guys did. For the shift 2 up and 1 right, did you guys take each of your representative points to do that?
Yeah.
Good. That's what I would have done too. So I would have taken this one and gone up 1, 2, right 1, which would have been like halfway in between, right? Which would have been the point 1.5.
2, 1.5.
And then 1. I think it's 1.5 and 1, right?
Yeah.
Because you go over 1, which would be 1.5.
Oh,
And
true.
you go up 2, which would just be 1. Now this one needs to go up 2 over 1,
Can't remember.
which would be the point 2, 2. And if you guys think about it, can't you just add 2 to the y and add 1 to the x? So adding 2 would be the positive 1, adding 1 would be 1.5, adding the 2 would be 2, adding the 1 would be the 2. So I can do that trick here, and I can say, okay, for the point 2, 1, adding 2 to the y would be 3, and adding 1 to the x would be 3 also. So I'm going to go 3, 3 for that last one. But what's one more thing that you should have drawn besides your 3 points? The vertical asymptote. What happened to him? Up 2, doesn't matter. He's infinitely high and low. But where else is he at? Right 1. The vertical asymptote is now at x equals 1. Then, swoop there. If you didn't shift your asymptote, you might have a logarithm that's going way too far to the left.
I'm sorry.
So for this one, just looking at the graph, hopefully you guys can also see why the domain is x greater than 1. Instead of being x greater than 0, like the domain of the original one. Since there was a shift right 1, the domain is now x greater than 1 instead. Okay. How many of you guys got that one mostly right, g of x? Mostly right. Like maybe one little baby mistake. Mostly right. You guys got the shift up 2 and over 1?
Yes.
Maybe the graph is a little fun. Okay, h. So we're going to start back from the blue, start from the parent function. We're going to vertically flip, which means vertically flip. Doesn't that mean all the y's need to have like the opposite sign? Okay. So if you want to think about it, we could go ahead and take a point like 2, 1, which was a point on the original graph, and we could say 2 things. We're going to flip the sign of y, but then what else do we have to do to the y? So you could just do it strictly mathematically and say, okay, I'm going to flip the 1 and I'm going to add 1. So what's the new point going to be? Another way of thinking about it is I could flip it down and then go up, and you're going to get to 2, 0. You could take another of the representative points, 1, 0, do the same thing. But what happens when you multiply 0 by a negative?
It's just 0.
Yeah, that's not very exciting. So negative times 0 plus 1. Well, flip it, doesn't go anywhere, and then up 1, well now he's here. Oh, I put 2, sorry, yeah, it's a 1. I don't know why I wrote 2 again. Sometimes our brains do funny things. There we go. Last but not least, we have this one, 1/2 negative 1. We could flip it, which would be 1/2 positive 1 and up 1. That's one way of doing it. Let's see if that matches up with what the math would say. Which would be, keep the 1/2, opposite sign of, so I multiply the negative 1 by a negative, and then I add 1 because the shift up 1. Did I end up at 1/2 positive 2? Yeah, I did. Now, kiddos, what are we going to do with the vertical asymptote if I need to vertically flip it and shift it up 1? Because if you flip it, isn't it still the same line? If you shift it up 1, it's still the same line. So I can say, oh, that one's going to have the exact same vertical asymptote. So I'm just going to do swoop, there it is, but it's the other direction, right?
There it is.
And that's H. We have F, we have G, and we have H. Not impossible. A little tricky though. But what are the key parts to a logarithmic graph that we need to have down in order to get the graphs okay?
Key point.
The 3 key points. I think the 3 help us with the swoop, and also the for the exponential, we had the 3 key points in the horizontal aspect. That's all we need. So, notes open, here we go. Let's just write down what can happen in a log. Just to remind ourselves, and you guys already did a few examples in your workspace. The nice thing is, you're going to have your spiral when you're doing your homework for sure. You can go back and look at it. And you should have your notes to help also. So what did you guys notice with the B on the outside? What was going on whenever there was something added or subtracted on the outside? Up or down. Shift, right? So you can say a vertical shift. But something that you guys saw in the workspace was, if there's a minus, remember, that doesn't necessarily mean, if there's a minus, it doesn't necessarily mean it's going to be a shift down. We can always rewrite this to be log base A of whatever the argument is. The point is what sign goes along with the B, not what sign is in front of the log. That might be a reflection, but what sign is in front of the B. It can be written both ways. What's going on with the C when you add or subtract on the inside? Oh, on the inside though. Yeah, horizontal shift. We didn't really talk about this one as much, the A. But let me just give you like a little visual for A really quickly. A is the base. If I was to do, for instance, like log base 2, I would have like the point 21. If I was to have log base 3, I still have the same intercept, but now I have the point 31. And that'd be 1/3 -1. If I was to have the log base 4, still the same intercept, but I'd have 4, 1. And 1/4 -1. Question, what happens as my base gets bigger?
It goes smaller.
It goes, or it like vertically shrinks, does that kind of make sense? So I just wanted to show you guys that as far as bases. As the base increases, the curve flattens. You could also kind of think about it as like a vertical shrink, I suppose. Kind of a little different because based on the bases, but it's still kind of the same idea. So I haven't shown you guys dilations. I haven't shown you guys like a stretch and a shrink. It can happen. They can put like a 2 times the log, which would make them like twice as high, the points, or like a 1/2, make the points 1/2 as high. It could be dilations. It's just not as common. Usually like the bases change, and as the bases change, it gets, well, how would you make the graph higher then? If the bases get bigger, or as the bases get bigger, the graph gets flatter, what's going to happen that makes the graph higher? Yeah, but what's something smaller than 2?
1.
Fractions.
But actually, 1's a straight line. He's kind of boring, because all of his powers don't work.
Negative.
Fractions.
Fractions would work. Like 1/2, 1/3, 1/10, 1/100, those would get really steep. Because you would go like 1/100th one, so it'd be going like really high like that. Negatives actually are a problem, because negatives, when you use negatives with exponentials, they flip-flop because of the signs. Messes everything up. How did flips happen in the workspace? What made a flip on that last one? Good. So whenever you have a negative in front. So if you have like a negative in front of the logarithm, that's going to be a reflection in the x-axis, which is the same thing as a vertical flip. Remember, multiply a negative on the outside, vertical flip, because if you think your x-axis, if you flip across, what's up is down, what's down is up. That's the reflection in or across or over the x-axis. What'd you say, Mike? Oh.
Can you continue?
See, I didn't watch enough of that show, actually. I think I watched the first, 4 episodes, and it got kind of weird. I guess that's the whole point, though, right? Stranger Things.
That's strange.
Yeah, exactly. There were things and they were strange. They got stranger.
So watch
Sesame
Sesame Street.
Street.
I love Sesame Street. Oh, baby.
Hey, that's where math first got fun,
I
right?
wanna go home.
It's fun, that's too, that's true. Then how do we get a horizontal flip, a reflection in the y-axis, or about the y-axis, over the y-axis, on the y-axis? You gotta put a negative on the inside.
Oh, baby.
Okay, got it? Reflections and translations, when they'll show up, how they'll show up, just gotta be ready. But guys, once again, for the logarithmic graph, the 3 key points really will help as well as the asymptote. For the exponential, the 3 key points will really help as well as the horizontal. The nice thing is, the 3 key points are related in both, just the exponential ones flip. The x's and y's flip for the logarithmic. The logarithmic ones flip for the exponential. All good things when thinking about studying if they're related, right? Okay, so once you guys have these, the examples for these are in the workspace in the back of your spirals if you need to access them. The ones that we just did a little bit ago, they're also in the notes, they're also in the video if you want to access them to help you with homework. If your notes don't quite cut it, if your workspace doesn't quite cut it. So I think I have one more example before we totally leave section 3.2. Oh, that's our one more example. I have one quick sketch I wanted to show you guys. But the nice thing is you basically already have this. I did it down, I just wanted to make it super clear. Sorry, Leah. On the next page, we've talked about it a few times. I'm just trying to show you how you can study with the graphing or how you can relate the two. Because the entire chapter, does anybody remember the chapter 3 title? Exponential and logarithmic, the entire chapter, we're just dealing with these 2 guys and all of their applications, okay? So you get to really, really focus on these and not really be distracted by tons of extra types of problems. But before we go any further, just to help with your guys' understanding, this is the exponential one, 2 to the x. The basic exponential that we talked about, the parent function we talked about, 2 to the x. This one actually gives us even more key points than I said in ours, but well, if I could trace it, that'd be nice. Well, that wasn't perfect either, that's okay.
There you go, you made it perfect.
Horizontal asymptote for the exponential. For those of you guys that can't see, I know it gets kind of weird with that light blue, so I'll write it 2 to the x. Having the points 2, 1, which would be right there. Having the point 0, 1, and having the point -1, 1/2. Those points really don't change as far as what they are with the exponential graph. When they go to logarithmic, they don't really change. The only thing that changes is the order. So instead of 0, 1, you have 1, 0. Instead of 2, 1. Did I switch that? I did switch that. That was 1, 2. Sorry. Change that guy. Plugging in the power of 1, 2 to the 1 is 2. I was giving you the logarithmic one. Now it's time for the logarithmic one. Instead of 1, 2, you get 2, 1. And instead of -1, 1/2, you get 1/2. Alright, boys behind me, you get very distracted very easily. I'm not calling out one specific, I'm just saying in general. Let's try to focus a little better. Flip it, flip it, flip it, and even with the asymptotes, flip it. They are inverses of each other, so we can literally say if we know one, we should know the other, we just have to flip everything. We just have to switch the x's and the y's, the horizontal with the vertical, because, once again, they are inverses. Because the x's and y's switch, because they are reflections across the y-axis. We've talked about the graph of logarithms today. We talked about transformations of logarithmic graphs today. We reviewed really quickly the relationship between exponential and logarithmic graphs and how they're inverses. So to end the section, we're going to review really quickly how this whole inverse relationship helps us when solving baby puzzles. Okay? How this relationship helps us when we're actually solving equations. So to help us with that, let's do this last example. And let's talk about how this inverse relationship helps us with problems too, not just with graphs being able to switch key points and asymptotes and all that jazz. As you guys look at the example on the board, if it says, hey, here's an equation, and guess what, x equals something, what should we always think of doing? Yeah, plug it in, right? We should always think of plugging it in. So, if we were to plug it in, y equals ln of who? True. And who is x that we're plugging in? Yeah, so our new input is e to the negative 4. Now, according to some of the properties we've written in our notes, that's all well and good. And maybe some of you could jump to the final answer. But let me show you something really quickly. Natural log is log of what base? We rarely write it, but sometimes it helps. What base does a natural log have? E. Because of the inverse relationship, and it's a property that you wrote in your notes, the inverse property, because of the inverse relationship of logs with exponentials, anytime you have log base a of a to the x, you can always say a log base a will undo an a to the x. Inverses undo each other in the equation. So if it undoes a to the x, we are left with, if you want to think about it, a log base a cancels out an a to the x. So that's the one way to undo, that's the one way to cancel out the base. If you ever want to cancel out an exponential, or even similarly, if you ever want to cancel out a logarithm, you need to raise the a to log base a. So this cancels out the exponential and the log just to get x, and this cancels out the exponential and the base just to get the x. So this is true, and if ln is a log base e, these two are inverses of each other. What can we say is the final answer? Got it. So whenever you have an ln of e, it's like they cancel out, because they really do undo each other since they're that inverse relationship. And all you have left is the power. If you would need to write out ln to be log base e, that also works. But the only way you can cancel out a base is with a log, and the only way you can cancel out a log is with a base. We'll work way more on that in section 3.2, which we're going to start today, but this finishes 3.2. There we go.
Yes.
So for tomorrow, okay, for today, you were allowed to have a little bit of grace to catch up on 3.1 for those of you that had all the tests and all the quizzes and all the craziness on Friday. For tomorrow, I need 3-2 homeworks. Wait a minute, this is homework 20, I think, right? Double check, did you guys name 3.2A number 19?
Yes.
Oh, it was 18?
No, this is number 20.
We'll double check.
I have it written down.
No, this is 19. 19.
I have 18 as 3.1, 19 is 3.2B, and 20 is, sorry, 3.2A, and 20 is 3.2B. I think that is.
That's a lot of homework.
Well, theoretically, it's not really that much unless you procrastinate. Rather you procrastinate, you have to catch up at some point.
I was supposed to start going with it, and I got cleaned until Sunday.
Alright, guys. Here we go. We're going to try and get through this page and the next one. 3.3, we're just starting, yeah.
We did procrastinate and did do 3.3A.
You can put them together in one homework, just name it homeworks 19 and 20 for 2 years, for them to understand. Someone just asked if they did procrastinate, they're doing all of 3.2 tonight. I said you could just call it homeworks 19 through 20 and just make it one big old section 3.2. That's okay.
Yeah, is it okay if they're still separated?
Totally fine. The TAs will expect them to be separated, so that's actually better. Alright guys, remember that hot day behind? We need to at least start 3.3 on a calendar. Now we are finally caught up. Today's direction was to start 3-3, tomorrow's direction is to finish, so we're finally caught up. I am writing down really quickly the change of base formula, just to remind you guys, if you do have a log of a certain base, you can change it to be a different base. If you take it of the old argument, and then take the log, the new log, over the old base. Log of the old argument over log of the old base. You guys don't really need to skip any of the lines. And to be honest, this is just showing you where a certain property that you learned last year comes from. But then after this page, after you see where it comes from, I'll just have you guys write down the properties and we'll use them. But this actually has to do with the extra credit problem, number 76 on 3.1. Because if you had done that problem, you would have seen, or even when you just checked it with me, maybe the rest of you guys that didn't even do that problem, when you add in the powers, where did that come from originally? What makes you add in the powers? Like, close, like bases, which is kind of like terms, right? So like bases. I would have needed to have a to the log base a of u and a to the log base a of v. So then we could separate that up. And then as we separate that up, do you guys see that inverse relationship, a to the log base a? And a to the log base a. What was I able to do just a second ago when I had ln of e, or log base e of e? I was able to cancel it out and steal the argument. If I have a to the log base a of u and a to the log base a of v, once again I have this relationship of the log being raised as a power of a. They're going to, since they're inverses, undo each other entirely. So all that's going to be left is u, and all that's going to be left is v, because of that inverse property. Now this is where it gets really crazy. Because of this substitution, I can say the following. If I do a to the log base a of u plus log base a of v, and if that truly does equal u times v, then I can go ahead and say, well, what if I were to get rid of the a? But what I do to one side, I have to do to the other side. So if I was to get rid of that a, I would just have log base a of u plus log base a of v, two separate logarithms, seemingly unrelated, being added, is going to equal log base a single logarithm of the product u times v. This is called the product property of logarithms, that you can condense two logs, same bases being added into the log of one product, or you can expand the log of one product into the sum of two separate logs of each of the factors with addition. And this leads us up to three important properties that work for any logs, and let's write them for ln's too, because sometimes people forget that ln's are really just logs. And this is where we end today. These three properties are the ones that we're going to be practicing with tomorrow, as soon as, or right after, we grade section 3.2, the homework that you guys are trying to catch up on tonight. Sound good? So, goal for you guys, catch up on 3.2, logarithms. We practiced some of the algebra today, we practiced some of the graphing today. You want to catch up on 3.2 so that you're ready to tackle 3.3 tomorrow and not have to start this week really behind. All right, cool kids? Technically, it's 5 more seconds, but now let's go ahead and get headed to chapel. Sound good? Bye, guys. Happy Monday. Hang in there. You guys seem kind of awake. Let's try to keep that up. Bye, Michael.